I'm starting my first exposure for the night. We are on IC 1396, or the Elephant's Trunk Nebula. My guiding looks great. 60 or 0.6 arc seconds total. A pretty decent guide graph. And Nina is great. You guys should really try Nina out. It's free. It does everything and more than APT. It's about as good as Sequence Generator Pro. I would say just about equal. You can't do like many complex sequencing with Nina that you can with SGP, but in my opinion, you don't need those unless you're running a remote observatory. Anyway, to each his own. I'll check back later. Thanks for watching. Okay, this is night 2. We are imaging in H-alpha. Last night I got 5.4 hours of data in the H-alpha filter on the elephant's trunk. And tonight I'm getting another 2.6 hours. That'll bring me up to a total of 8 hours. And then I'll still have a good 3.5 hours or so before this thing sets. And so I'll be switching over to a sulfur, and I'm going to start the sulfur filter data collection tonight after the H-alpha is finished tonight. The data's looking good. You can see my last exposure right here in Nina. The stars are nice and round. The guiding is good. Let me zoom in here. I'll show you. Nice round stars all the way in. Look at that. And that's what I like to see. Perfectly round, circular, well-focused stars. All right, folks. Well, I'll be back later. Thanks for watching. Introduction to Astrophotography. I like this animation. It shows light of all colors coming off the sun and scattering through the atmosphere. If you have a lady on the bottom right, I chose this character because of the obvious spread of colors. She has a red blouse or shirt on. She has tan skin and dark hair. The light from the sun bounces off of her, reflects off of her, and those photons travel towards a DSLR camera, traveling through the lens and onto the sensor. Now you can see the image formed of this lady on the sensor right here. And what's happening is pigments in the shirt, such as red, they are absorbing all colors except for red. They reflect red. The blues and greens are absorbed. And so that's why we see red. It's the only color or combination of colors that results in red that's reflected. Okay, so we have the sun and stars, those emit their own photons, galaxies, and then nebulae. These are all examples of some astrophysical objects which emit their own light through various means. Here's an animation that shows the excitation of a hydrogen atom. The photon is kicked up to a higher orbital and then spontaneously decays back down and emits the characteristic wavelength of light for that atomic orbital transition, and you get an emission spectrum from that emitted light. And if you're looking through a cool atomic gas at a continuum spectrum of light from, say, the sun, or some other conglomeration of stars, you will get an absorption spectrum. That is the continuum spectrum of light with the atomic emission lines removed. Now, when I was a kid, I always wondered, how in the world does the absorption spectrum work? Because if it emits and absorbs at the same exact wavelength, by definition, then how is it subtracting? Wouldn't it just emit that light that it absorbed and it would rejoin the original incoming continuum spectrum? Well, the answer is that the atom does not have a preference as to what direction it emits that line of atomic transition. That emission line is emitted randomly. It doesn't know, quote, quote, or care what direction the original light was going. So it's not going to send that photon directly towards you. It's going to, more likely, because there's so many more directions that are not pointed towards you, not directly towards you, especially if it's hundreds or thousands of light years away, it's going to not be along your line of sight. And so it is, in fact, removed, subtracted from the incoming continuum, and you indeed get the absorption spectrum. Now, with this example of the Rosette Nebula on the bottom right, taken by my friend John Soika Jr., he has selected a hydrogen alpha filter to highlight the features of this cloud, the hydrogen cloud here shown with the Rosette Nebula. And so the universe is vastly composed of hydrogen, at least in terms of regular matter, and this hydrogen gas has a number of Balmer series transition processes that it can undergo, and one of them is the 656.3 nanometer pinkish red emission line. It's called hydrogen alpha. It is a atomic transition from the n equals 3 to the n equals 2 atomic state, the Balmer series. And this animation that's been playing for a while shows the production of an emission line spectrum and the absorption line spectrum from a continuum light source.